based on the name, the inert components are those in the coal that neither fuse nor cohere during the coking process. The inert components originate from coal formed when the plant material was not immediately buried underwater, but instead was exposed to the atmosphere, resulting in oxidized residues. A more typical and easily understood example is the charcoal left over from a forest fire. Charcoal is a typical example of inertinite. If you pick up a piece of coal, we can clearly see layers of coal inside with a silky, fibrous luster. That is this substance. Because it has already gone through combustion, or what we call carbonization, the carbonized coal has lost its effective volatile components. So, when it enters the coal body, it is already a substance primarily composed of carbon structure. The technical properties of pure inertinite change very little from brown coal all the way to anthracite. However, because the oxidation process is sometimes incomplete, there can still be some variations in volatile matter and caking properties. From the perspective of coking science, to form good coke, you cannot rely only on active components. It must also have inert components. That is to say, a proper ratio of active and inert components in the coal is one of the prerequisites for producing good coke. Therefore, we should not consider the inertinite component to be a bad thing in coal. It is analogous to the pebbles or aggregate in concrete, with the active components being the cement. It acts as the aggregate. In this sense, every material component in coal has its necessity and rationale for existence. This is because to produce qualified coke, there must be an appropriate proportion of active and inert components. However, the inert components cover a broad range. Meager lean coal, meager coal, and anthracite all belong to the inert component category. During the coking process, they can all serve the role of the aggregate. But when we observe them under a microscope, we find that inert components like meager coal or lean coal undergo effective fusion and bonding with active components during coking. However, when we observe inertinite under the microscope, especially looking at the microstructure of coke formed from pyrolyzed inertinite, it still retains the original state of the inertinite. That is to say, it has not achieved better fusion and carbon bonding with the other components. It has not changed its own state. Therefore, under the same active-to-inert ratio, inert components like meager coal or lean coal can achieve a better coking result than natural inertinite.